Hello everyone, my name is Salomon Edimo. I am a PhD student at the Universidade Estadual de Campinas, and as part of the 2025 Energy Simulation Summit, it's an honor for me to present you this poster part of the work we have been developing. The title of this poster is Model-Based Evaluation of Permeability Effects on Foam-Assisted Water Alternating Gas FAWAG Performance in Brazilian Pre-salt Carbonate Reservoirs. So the background of this study is typically the Brazilian pre-salt fields, which are which have a huge hydrocarbon potential. They are offshore carbonate formation with high level of heterogeneity and presenting high oil with high CO2 content, and it has a certain potential for gas-based EOR to fit the environmental and the logistic compliance. In terms of potential recovery methods that can be employed in this Brazilian pre-salt field, we have the water alternating gas WAG, which is a well-known technique, but which may suffer from some viscous instabilities. More recently, what has gained momentum is foam flooding techniques such as foam-assisted water alternating gas, also called FAWAG. It has the potential to mitigate disconformance and mobility issues by controlling gas mobility and therefore enhancing enhancing the gas superficiency. FAWAG is a technique that has the potential, as we said, to enhance the superficiency, but may suffer from injectivity and foam stability challenges. So it's not a perfect technique, but it's a technique that is which has gained a certain momentum, that has drawn a certain attention in the recent studies. So what motivated our study typically is the study of permeability effects on FAWAG performance, particularly in naturally fractured reservoir, which may be a key geological uncertainty and that may have diverse variations in terms of magnitude, spatial distribution. We refer here to the heterogeneity, and also the fracture to matrix ratio. Also, there have been some core scale findings related to the permeability effects, but there is a limited translation of this finding to field scale regarding the scale difference, of course, and also the multi-scale heterogeneity which cannot be addressed at core scale. Also, most FAWAG studies focus on homogeneous and midly heterogeneous media, whereas in the pre-salt we have ultra heterogeneous settings. Additionally, fracture matrix interaction may significantly impact foam flow, and this has been thoroughly studied in the current literature. This study is particularly important in the Brazilian pre-salt context because these reservoirs are often fracture dominated and present high heterogeneity and complex carbonate conditions. The objectives, therefore, of our study is to expand foam behavior understanding from lab scale to reservoir scale by assessing the permeability effects on foam strength in pre-salt setting, and also evaluate FAWAG's relative performance to a well-known and ongoing technique in the pre-salt, which is WAG, water alternating. To address this objective, we employed the following methodology, starting with the selection of a base case study, which is a case study coming from existing study developed within our research group. Then we go to the selection and of the property to analyze, and if, as we have different property, we will run a one factor at a time sensitivity analysis where we will focus solely on one property at a time to avoid any cross effects between properties and therefore prevent any future bias in our analysis. From this property we selected, we generated case studies for a sensitivity analysis and a result comparison. We mentioned initially, we have been mentioning what case study, but a case study, what it is simply a reservoir model and its injection scale, which may be water injection WAG or FAWAG. It can be different. So in the application part, our work will focus on a synthetic model of a real pre-salt characteristic. We focus particularly on a sector model from a full field. This enables us for a detailed analysis of the ongoing phenomenon in this sector. And this sector is a dual media with porosity and permeability for matrix and fractures, which is particularly interesting in the context of naturally fractured reservoir. In terms of reservoir characteristics, we have the porosity and the directional permeabilities for both media, matrix, and fractures. About the injection cycles, we are employing a 7-month injection cycle for both recovery methods with either WAG or FAWAG. With WAG, we start with 6 months of water, then 1 month of gas CO2. While for FAWAG, we start with 1 month of water, followed by 5 months of surfactant injection with a concentration of 1 weight%. And finally, we inject 1 month of gas CO2. To quantify here, one key effect when in foam flooding, it is the reduction in gas mobility due to foam. We will employ here this metric called gas resistance factor to flow, which can be given in terms of mobility, which is the ratio of gas mobility by the foam mobility. This is particularly employed in numerical reservoir simulation studies. In terms of pressure drop, it can also be employed, but usually this approach is usually employed for core scale studies. In terms of permeability modification, we employ in this study, as we already introduced, we focus on in terms of permeability variation in magnitude, spatial distribution means heterogeneity, and fracture to matrix ratio. And for FAWAG, to evaluate FAWAG's relative performance to WAG, for any matrix X, we will use simply this formula. Result we obtain first up will be on the permeability magnitude effect, which here we use the scaling factor called A, which from the existing existing permeability to the new permeability we calculated based on the scaling factor, which variation is from 0 to 4. We can observe here on this graph that with the increase of the permeability scaling factor, which means the case study are getting more permeable, we can notice here the gas resistance factor to flow keeps increasing. We also notice a similar trend here on the relative variation of GOR when we compare FAWAG to WAG. It keeps increasing and it's always positive. But there is a sign minus here, which shows that, just to indicate that FAWAG's GOR means gas oil ratio is always lower than WAG's GOR, as a sign of effective gas mobility control. So these two behavior correlated. We notice that FAWAG may outperform WAG in low to moderate permeability reservoir due to the development of stronger foam, as we observe here on the curve of on the evolution of the gas resistance factor to flow. However, as we may notice here on the variation of cumulative oil production, at an extreme case where we are in very high permeability setting, we notice that this relative difference goes to negative, which shows that WAG is regaining advantage over FAWAG. The second property that may draw our attention is the permeability distribution, which means also heterogeneity effect. Here we used a shifting factor called B related to the permeability offset. With the shifting factor, we may alter the permeability distribution, and by altering permeability distribution, we also alter the reservoir heterogeneity. Or we can notice that is with the increase of the permeability offset, it means the reservoir is getting more homogeneous and more permeable. The foam is getting stronger. We have an increase of gas resistance factor to flow. However, in this context where the reservoir is getting more permeable and more homogeneous, there are less challenges to gas flow. You may have less channeling. As a consequence, WAG is regaining some advantage, and we have here the GOR variation, which is decreasing. as indicating that we have less challenges to gas flow. In terms of the relative difference in terms of cumulative oil production, in this case where the reservoir is moderately permeable and heterogeneous, we have the cumulative oil production, which is shows moderate fluctuations, which shows that FAWAG is outperforming WAG. However, in this extreme case where we have the lowest permeability offset, which indicates that here the reservoir is less permeable and less homogeneous. In this context, there are several challenges to flow and particularly to gas flow, and here FAWAG is underperforming WAG. The third and the last property that we analyze is the fracture to matrix permeability ratio effect, where we use this factor C to show the permeability contrast of the ratio between fracture and matrix. What we can notice is that all the curves, it means the gas resistance factor to flow, the GRFF, the relative difference in gas oil ratio GOR, and the relative difference in cumulative oil production, these three exhibit a similar trend. They are all increasing with enhanced fracture to matrix permeability ratio, which may suggest that FAWAG effectivity is enhanced also as foam strength with higher fracture to matrix permeability ratios. However, if we take a close look here at very high permeability ratio starting at 100, we are noticed that there is a plateau-like behavior here, also here on the variation of GOR and also on cumulative oil production, which may indicate the emergence of challenging conditions for FAWAG efficiency, similar to an asymptotic trend. So at extremely high fracture to matrix permeability ratio, we may have a decrease beyond a certain threshold, as it has been suggested by Joseph and Nal in 2024. To conclude this presentation, given the specific condition in this study, it means on a controlled case study with real pressure characteristics, we have shown that moderate heterogeneity and permeability may favor foam strength and its stability. FAWAG may underperform WAG under extreme conditions. We have mentioned in terms of permeability and heterogeneity, and ultimately fracture and matrix interactions are critical in FAWAG implementation, as we have seen that at certain value of fracture to matrix permeability ratio, FAWAG efficiency may be particularly enhanced. So we would like to thank the different partners and different bodies involved in the development and the support of this work, and we would like particularly to thank Native Simulation for the opportunity to present this work we have been developing. So thank you everyone.